Hi everyone, this is your Tobacco Auctioneer Test 3 review for Physics 2010 in fall of 2021. So logistics, it's going to be very similar to the last test. Remember that you're allowed a 3-inch by 5-inch note card for an equation sheet. Please don't bring any tablets, PCs, or cell phones. You need to bring a regular old calculator with no access to the internet to do the problems. Okay? Now we've covered Chapter 7, Chapter 9, and Chapter 11, which will be on the test. We did a little bit of coverage of Chapter 10, and that might end up as an extra credit question on your final, but it won't be on this test, okay, because we haven't had a chance to do the homework. In Chapter 7, that was on internal energy. We covered pretty much the whole chapter, and we also supplemented it with some stuff about the damp-driven harmonic oscillator from your supplementary text K and K. We skipped Chapter 8, that's modern physics stuff. Chapter 9's covered except for Section 4, and we really expanded discussing moments of inertia and spherical coordinates. In Chapter 11, we covered the whole chapter, and remember, I'm not going to test you on phy2010. Now, if you're wondering what questions are going to appear on the test, I can tell you 2 of them for sure. You are going to have to find the moment of inertia for a symmetrical object. I'm not going to tell you which one, but you're going to have to do the full proof with the integration and all that jazz. So make sure that you know how to do the examples that I did in class and the ones that I assigned you for homework. You're also, I promise, going to have a problem on a damped harmonic oscillator or a damped-driven harmonic oscillator, so study those quality factors. Okay, Chapter 7 on internal energy. Let's go. The internal energy is basically the energy of the system that's associated with the microscopic components, the atoms and the molecules, and it's due to the kinetic energy, the motion, or the vibration of it. The internal energy is often associated with temperature, which is how hot or cold an object feels. It's a measure of the internal energy, but remember that it is not the same thing as the internal energy. They're linked via some formulas that you'll learn about in thermal physics. The SI unit of temperature is the Kelvin, and you can convert in this way. Now, dissipative forces can pull kinetic and potential energy out of the system and convert it into internal energy, which increases the temperature of the object and the surroundings. And that's covered in the first law of thermodynamics, covered in thermal physics. If the temperature of an object changes, we can relate it in this way. The change in the internal energy of the object is equal to mc delta T, where m is the mass, c is the specific heat, and delta T is the change in temperature. The power is the time rate of energy transfer. Power is basically energy divided by time. The instantaneous power is dE dt, or the time derivative of the energy. And using work as the energy transfer method, it could also be written as the derivative of the work with respect to time. If you do that one, the derivative of the work with respect to time, and it's the force that's doing the work, and the force is a constant force, then your power could be written as F dot V. Now, the SI unit of power is the watt, which is a joule per second, but there's other units of power, like the horsepower, which is 746 watts. You can also convert power into energy by multiplying power times time, and this is a unit of energy that you might find on your power bill, like kilowatt hours and stuff like that. 1 kilowatt hour is 3.6 times 10 to the 6 joules, by the way, but you just get that by multiplying a kilowatt, which is 1,000 watts, times the number of seconds in an hour, which is 3,600 seconds. We talked about dissipative forces. Specifically, we discussed drag and viscous friction, which is one form of resistance that a medium would provide to something moving through it. They oppose the instantaneous velocity, so they will always work to oppose the change in motion. You use the formula for air resistance for high-speed, high-density objects, and that one's the one that's proportional to the speed squared. The drag there is equal to 1/2 c rho AV squared, where c is the drag coefficient. C here is the dimensionless drag coefficient, okay? Rho is the density of the medium, A is the cross-sectional area, and of course V is the speed. Now what will happen is an object will begin falling through air when you drop it, and it'll pick up speed due to the force of gravity pulling on it. But air resistance will oppose that, and so what will eventually happen is that the speed will grow to the point that the resistive force is equal and opposite to the force of gravity, and at that point the object will no longer accelerate. This velocity is called the terminal velocity, and the formula for the terminal velocity, v sub t, is the square root of 2 mg, that's supposed to be a c there, that's a typo, over c rho a. Viscous friction is linearly proportional to the velocity. This is the kind of thing that you'd have for smaller or lower density objects and lower speed or more viscous media. In this one, the formula for viscous friction is F is equal to minus CV, where C here is the drag coefficient again. Usually we use a lowercase. It just auto-corrected me to a uppercase, so it's supposed to be C like that. Now, it's not going to have the same value of the drag coefficient. It's not even got the same units, okay? In this case, the terminal speed would be mg over c, okay? The speed for a horizontal object in the absence of other forces will decay exponentially with time due to the drag if it's under viscous friction. And then you just have an exponential decay of the instantaneous, or the initial velocity vi. It's going to be v of t is equal to vi times e to the minus t over tau. Tau here is the time constant, which is m over c, the mass divided by the drag coefficient. If it's falling under the influence of gravity, the velocity will look like this, g tau times 1 minus e to the minus t over tau. And remember, we derived those equations in class. We used this viscous friction when we were talking about damped harmonic oscillators. So remember that we took a deep dive into the harmonic oscillator here. First, a review. The period t is the time interval required for the particle to go through one full cycle. That's equal to 1 over the frequency. And the frequency is also equal to the angular frequency omega divided by 2 pi. Remember that for a simple harmonic oscillator, the angular frequency was omega naught squared is equal to k over m, or omega naught is equal to the square root of k over m. If you have a simple harmonic oscillator, which is only under the force of the spring, right, then that is a sinusoidal function. We described the position as a cosine omega t plus phi, where phi is the phase constant. Then the velocity would be the time derivative of that, minus omega a sine omega t plus phi, and the acceleration is the time derivative of that, minus omega squared a cosine omega t plus phi. Remember that simple harmonic motion is not uniformly accelerated motion, and so you can't use the kinematics equations to describe it. You have to use the ones that you see here. Remember that you can solve for the phase constant if you're given the initial conditions. If the object's at its max displacement at t is equal to 0, the phase constant is 0. But if not, then you can use the initial value of the position and the velocity to solve for what the phase is. And we did some examples of that in class. The energy of a simple harmonic oscillating system is the sum of the kinetic plus the potential energies. Since the elastic potential energy of the system is 1/2 kx squared, and the kinetic energy is 1/2 mv squared, then, using the expressions for x and v that I showed you on an earlier slide, we can show that the total energy is constant in time for a simple harmonic oscillator and is equal to 1/2 ka squared, where k is the spring constant and a is the amplitude of oscillation. Remember that in a simple harmonic oscillator, there is no damping or driving forces, and so the amplitude is constant. If you look at a plot of the total mechanical energy, which would be a sum of the kinetic and the potential, then it's going to be a constant. But as the object moves through the max displacement to the, say, max displacement in the other direction, then the kinetic and potential energies will exchange energy between them. The kinetic energy will be its max when the particle is at equilibrium, and the potential energy will be at its max at the extrema. Remember that if you had a vertical spring hanging under the influence of gravity, that what that's going to do is change the equilibrium position of the mass to be mg over k below the unstretched spring length, okay? Below if the mass is, say, suspended from a spring attached to something vertical. If it's a spring attached to a table and then the mass is above the spring, then it would be depressed from that there, okay? Now, the mass is going to oscillate about that new equilibrium. But enough with simple harmonic oscillators. Real harmonic oscillators actually have friction and damping, and so in this chapter we discussed that. The only analytical solution that we have, the one that we can solve for theoretically, is viscous friction, and all others have to be numerically solved. If you're solving the viscous friction one, the differential equation that you're solving is the mass times the acceleration, and ma is equal to minus kx minus cv. And remember that we went through the guess and check method for this. The solution to the equation is x of t is equal to a times e to the minus gamma t over 2 times cosine omega t plus phi. Remember that gamma is the drag coefficient c over m. Omega naught squared is k over m, but that would be shifted. Your actual frequency of oscillation would be shifted from what it would be for a simple harmonic oscillator by the amount omega is equal to the square root of omega naught squared minus gamma squared over 4. And phi, yet again, is the phase constant. Now, since system is damped, the energy is not going to stay constant. It's going to get sucked out and transferred into internal energy. And so you're going to have a decay, an exponential decay of the average energy. And that looks like the energy with respect to time on average will be E naught times e to the minus gamma t. Okay? We also define the quality factor, which is a measure of the damping. And the quality factor big Q is equal to omega over gamma. We talked about damp-driven harmonic oscillators too. So in this case, we solved for a driving force that was sinusoidal in nature, F naught cosine omega drive times T. Omega drive doesn't have to be the same as the natural resonant frequency of the system. Remember that. So we modeled this for a damped-driven harmonic oscillator. So we still had viscous friction acting on it, and so the differential equation was MA is minus KX minus CB plus F naught cosine omega dt. And we found a solution of x of t is equal to a cosine omega dt plus 5. In other words, we decided that after a long enough time, the system would oscillate at the drive frequency. Okay, there might be some transient stuff that isn't solved by this, but we didn't worry about that. We just worried about the steady state solution after the system had settled into some kind of equilibrium oscillation condition. Now, we derived the equations for the amplitude A of the damped-driven harmonic oscillator and for the phase. The amplitude was equal to F naught over M divided by the square root of omega naught squared minus omega drive squared plus gamma squared omega drive squared. The phase constant phi was negative gamma omega drive divided by omega naught squared minus omega drive squared. Here, of course, F naught is the magnitude of the drive force, the max drive force. M is the mass attached to it. Gamma is the damping coefficient C over M. Omega naught's root K over M. And that's the natural frequency of the oscillator for a simple harmonic oscillator. And omega D is the drive. Remember that the drive frequency, as it gets close to the natural frequency, is going to have a huge amplitude response. And this is called resonance. The curve, if you plot it out, is going to be a Lorentzian function. It's also the same kind of function, by the way, that you see in energy spectra. Now, people look at the width of that curve at half of the peak maximum, and that's called the full width half max. And you can find the quality factor by measuring the full width half max. The quality factor, which is omega over gamma, will be equal to omega, which is close to omega naught for a lightly damped oscillator near the drive, omega naught over delta omega, where delta omega is the width of the curve at full width half max. Okay? So, that was chapter 7. I promise, you're going to have a question on damped harmonic oscillators, maybe damp-driven harmonic oscillators. Chapter 9, rotational, translational, and vibrational energies. So first of all, we talked about relative motion by discussing Galilean relativity. So you have two inertial frames. The inertial frames mean non-accelerating, and those are described by S and S prime. S prime is the moving frame. It moves with constant velocity u with respect to S. It doesn't have to be along the x-axis, but remember you can rotate your coordinate systems however you like if you're setting up the problem. The deal is that you're going to assume that the origins of S and S prime coincide at t is equal to 0. That's a very important assumption. And an observer in S describing an event is going to use space-time coordinates x, y, z, and t. An observer in S prime is going to use space-time coordinates x prime, y prime, z prime, and t prime. If you're going to relate those two things, the relationship for describing the position in one frame with respect to another will be r prime, the coordinate in the moving frame, is equal to r minus ut. The velocities in the frames can be related to each other by simple addition. V prime is equal to v minus u. The total kinetic energy of a system is the sum of the translational kinetic energies about the center of mass and the relative kinetic energy of the system's components about that center. So your center of mass motion, kinetic energy of that, plus the motion about the center of mass. So your total kinetic energy, K tot, is equal to K trans plus K relative, which would be the sum of 1/2 times the sum over mi vi squared, where mi are all the little masses and vi is their respective velocities. Now, K relative can be either a rotational or vibrational motion of the constituents of a system. You can write the momentum of the system, momentum of the center of mass as P cis, which is going to be the total mass, big M tot, times the velocity of the center of mass. And therefore, K translational could be written as the magnitude of the momentums of the system squared divided by 2 times the total mass. You can find the center of mass velocity by the equation V center of mass is equal to the sum of mi vi divided by m total. And the relative velocity of the particle is the velocity of the particle minus the velocity of the center of mass. So that would be vi minus vcm. So that means that the relative kinetic energy will be the sum of over mi times vi relative squared, which is k total minus k translational. An object rotating about an axis with an angular speed omega has rotational kinetic energy even if it doesn't have any translational kinetic energy because its center of mass doesn't move. Each particle is still going to have a kinetic energy of 1/2 mivi squared. Remember that if it's moving in rotational motion, you can substitute vi is equal to omega I times r, where omega I is the angular speed, angular velocity, and r is the distance from the axis of rotation. So if you write the total rotational kinetic energy of a rigid object, then it would be the sum of all the ki's, which would be the sum of 1/2 mi ri squared times omega squared. Now you can take the 1/2 and the omega squared, right? That's the things that are constant for all the particle. Pull those out, and then what you're left with is the sum over mi ri squared. That is the moment of inertia. So the definition of our moment of inertia for a point mass system is I is equal to the sum over mi ri squared. Its SI units are a mass times a length squared, which is kilograms meters squared. And don't forget that this is the distance from the rotation axis that you're plugging in here. Now, if you have a continuous object, it's more convenient maybe to write it in terms of an integral instead of a summation. So in that case, I will be equal to the integral of r squared dm. Now, it's stupid to integrate over mass. So instead, we integrate over the spatial coordinate and use the mass density to convert. And so that means that I, for example, for a 3D object would be r squared times rho dv. Now, you can either have a volumetric mass density, where dm is rho dv, or a surface mass density, like a sheet or something, and that sigma is the mass divided by the area, so dm is sigma dA. Or you can have a linear mass density like a rod or a chain, and there lambda is equal to the mass divided by the length, and then dm is equal to lambda dl. We talked about and solved for the moments of inertia for various rigid objects. I did some and you did some for homework. In class, I did the hoop, the solid cylinder, the long thin rod, and the solid sphere, and you did the rectangular plate and the thin spherical shell. And you have to know how to do all of those and recreate them. I promise you one of those will be on the test. Remember that if you're not rotating about one of the axes of symmetry, then you can use the parallel axis theorem, which states that your new moment of inertia will be the center of mass moment of inertia plus md squared, where m is the mass of the object and d is the distance from the center of mass axis to the arbitrary axis. We went over cylindrical coordinates. Cylindrical coordinates use r, theta, and z instead of x, y, z, and you convert back and forth from Cartesian to cylindrical via the equations x is equal to r cosine theta and y is equal to r sine theta. Remember that theta is measured counterclockwise from the plus x-axis. Now, if it's been a while since calc, you might need a refresher in spherical coordinates. Spherical coordinates, instead of Cartesian, go rho, theta, and phi, okay? So rho is the distance from the origin to the point in question. Theta is the angle that swings counterclockwise from the plus x-axis to r. It's the same as in cylindrical coordinates. And phi is the angle that swings down from the plus z-axis to the position vector. The volume element in spherical coordinates is dv is equal to rho squared sine phi d rho d phi d theta, okay? Don't get confused here. So this rho is your spherical coordinate and density rho, that's different, okay? Okay, if you model a system as a point particle, you can apply the work kinetic energy theorem to find the net change in the translational kinetic energy of the center of mass. We talked about this way back when. That means that delta K trans is going to be your net force dotted with your displacement, assuming that your net force is constant. If it's not constant, you have to perform an integration of the force over the displacement. Now, this is always true, but if you have a system that can't be modeled as a point particle, then maybe it's not the whole story. So, if you've got a system that is an extended body and isn't well served by the point particle model, then you can use this equation here. The change in energy of the system will be equal to the change in the kinetic translational energy plus the relative kinetic energy plus any change in potential energy plus the change in the internal energy, and that will be equal to the sum of the works, okay? What you do for these is you model your system as a point particle, okay? and you solve for the problem that way, getting the network and finding the change in the kinetic translational energy, and then you model the system as an extended object, okay? And once you do that, then you can solve for the change in the internal energy, for example, or the relative kinetic energy. So we did a bunch of homework problems on that, and you should study those, like the yo-yo problem and the springs and all that good stuff. Okay, Chapter 11 covers angular momentum and torque. So first we had to review cross products. Remember your right-hand rule. You've got your stop in the name of love, and you got the gun. So those are your two ways. So for stop in the name of love, you take your right hand, and point your fingers of your right hand in the direction of vector A. Swing your palm towards vector B, and your thumb will be vector C, your resultant vector, okay? If you're doing the gun one, you make the sign for loser in any direction. A is your index finger, B is your middle finger, and thumb is your resultant. If you want to find the magnitude of the cross product, the magnitude of the cross product for C is equal to A cross B would be AB sine of theta, where theta is the angle in between A and B. Now, another way to find the cross product is to use determinants for the 3x3 matrix. We discussed that in class. Okay, so you might need to know how to do that. Remember that the reason we did all this is because angular momentum and torque are cross product kind of formulas. So the angular momentum of an object moving about some origin would be L is equal to R cross P, where R is the position vector for the object and P is the momentum. So the SI units of angular momentum are kilograms meters squared per second, and of course it's the kind of momentum that is dependent upon your choice of origin, because R changes as you change your origin, so just remember that. If you're finding the magnitude there, it's going to be mvr sine of theta. If something is traveling in a circle, then theta is 90 degrees, and so you just have mvr. L is going to be perpendicular to the plane formed by R and P. And for a lot of problems, L is going to point along the rotation axis, okay? Now, angular momentum obeys superposition, which means that your total angular momentum will be the sum of all the angular momenta from all the different parts of the system. So you just add them up. If you break the position vector into components parallel and perpendicular to the momentum, or vice versa, then you can see that the angular momentum magnitude could be written as L is equal to R perp P. And here, R perp is your lever or moment arm, okay? And it's the portion of R that's perpendicular to P, because that's the only part that contributes due to the sine theta. Now, the angular momentum of an extended body could be written as L is equal to I omega, where, of course, I is your moment of inertia and omega is your angular velocity. So the rotational form of Newton's second law is also valid for a rigid object rotating about a moving axis, provided the moving axis passes through the center of mass and is a symmetry axis. So if L is equal to I omega is used, then that's the way the axis of rotation is directed by the right-hand rule. So for this right-hand rule, remember, you take your right hand, you curl your fingers in the direction of the rotation, and then your thumb is the direction for omega and L, all right? Now, the kinetic energy, as expressed in terms of L and I, K would be equal to 1/2 L squared over I, or 1/2 I omega squared. Now, if something is moving through space and rotating, okay, like say the Earth in its motion about the sun, it's rotating on its own axis, that would be its L rotational, and it also is moving in a near circular orbit about the sun, and that would be its L translational. So to find the total angular momentum of the Earth, you would just sum those two things up. Now, torque, that's the tendency of a force to rotate an object about an axis. It's a vector. In the magnitude of torque would be RF sine of theta, where R is the vector that points from the rotation axis to the point of application of the force. F is the force, and sine here is the angle in between R and F. You can also talk about R times sine of theta. That gives you D. That's R perp. Basically, that's the moment arm of the force. So, no surprise here, torque is equal to R cross F. It's the cross product of R with F. The units of torque are Newton meters. Even though Newton meters is technically the same as a joule, we don't call it a joule because torque is not an energy, okay? Torque is a vector, for one thing, and energy is a scalar. And that's just one of the many myriad differences between torque and energy. Now, force can cause a change in translational motion. but they can also cause a change in rotational motion, and that depends on the force, its direction, and the moment arm, okay? The torque is related to the angular momentum by the equation torque is equal to dl dt, which is equal to r cross f, which is equal to I alpha. And sometimes, when you're solving problems, you need both these equations, r cross f and I alpha, in order to finally solve, and then you set those two things equal. So don't forget about how to do those kinds of problems, which we covered in homework and in class on examples. Now, this is the rotational analog of Newton's second law. Remember that F is equal to dp dt, that's Newton's second law, and torque is equal to dl dt. So the force is the time rate of change of the momentum, and the torque is the time rate of change of the angular momentum. And there you go. So, for torque problems, you got to draw your free body diagram, right? Make sure to draw as an extended object or it's worthless. Label all the forces acting on the object, identify your rotation axis. This should probably also be your origin, by the way. And remember that torques cause counterclockwise rotations are positive and clockwise rotations are negative. You then sum all your torques to get the net torque, okay? And then you have several expressions for torque which you can use and solve for your unknowns. Now, if the net torque of a system is 0, in other words, there's no external forces causing a rotation, then that means that angular momentum is conserved because torque is equal to 0, which means dl dt is equal to 0, which means L is a constant, or L initial equals L final. And we did a whole host of problems on those. So, remember, if the mass of an isolated system undergoes some kind of redistribution, like the kid that was standing on that little merry-go-round and walked from the edge of the merry-go-round in towards this axis, right, that redistributes the mass. That changes the moment of inertia. And conservation of angular momentum then requires a compensating change in the angular velocity. So you set I initial omega initial equal to I final omega final, and that'll be some constant value, okay? So make sure for your angular momentum conservation problems to draw a picture if it's possible. Draw it as an extended object. Label all the constituents and any changes to the system. Identify your origin in the picture. Then find the initial angular momentum for each of your system constituents, right? Like the kid in the merry-go-round. You had an angular momentum for the kid and an angular momentum for the merry-go-round. You had to sum those up to get your initial angular momentum. Remember, clockwise rotations are negative, counterclockwise are positive. Sum them all, get your initial angular momentum. Repeat that for your final angular momentum. Remember that sometimes you won't know one of the things, and so you'll have to leave that as a variable, and then you'll solve for that variable, okay? So we've got some conservation laws. For an isolated system with no dissipated forces, energy is conserved. For a system with no external forces, like in collisions or something, linear momentum is conserved. And then angular momentum can also be conserved if there's no external torque. So there you go. Remember, we talked about this just briefly, but your angular momentum isn't always parallel to the rotation axis. It doesn't have to be. If it's not rotating about an axis of symmetry, then it's not going to point along the rotation axis. And that means that, ladies and gentlemen, you need to have your wheels aligned every once in a while. Okay, Chapter 10, Collisions. We talked about collisions. There's elastic and inelastic collisions. Inelastic collisions do not conserve kinetic energy. Elastic collisions do conserve kinetic energy. Remember that all collisions conserve momentum, so momentum is always conserved, but kinetic energy isn't. If you have a perfectly inelastic collision, that's one where the two objects collide and then they stick together and they move with a common final velocity. So here's a little schematic of that. Remember, momentum is still going to be conserved, even though it's inelastic. It's just kinetic energy that's not conserved. And so if you have two bodies, for example, m1v1 plus m2v2 is equal to m1 plus m2v final. Remember, momentum is a vector, so it doesn't have to be 1D like this. It could be 2D or 3D. It's still the vector here, okay? You're good to go. Now, if it's an elastic collision, then that means both momentum and kinetic energy are conserved. So you've got your momentum equation, which you had already, and in addition to that, you've got your kinetic energy conservation. If you've got two bodies, that would be 1/2 m1v1 squared plus 1/2 m2v2 squared is equal to 1/2 m1v1 final squared plus 1/2 m2v2 final squared. Remember that what goes into these equations is the speed, which would be the dot product of the velocity vector with itself. So for collision problems, you've got to, from context clues, sometimes they'll state it right out, but from context clues, identify whether the collision is perfectly inelastic, or elastic. Identify your system constituents, right? Pick an origin, draw yourself a picture. Write the initial momentum vectors for all of the system constituents and sum those momenta to get the total initial momentum. Repeat for the final momentum, and then conserve momentum by setting initial equal to final. Now, if you've got a 1D problem, it's just going to be one little equation. But if you've got x, y, and z components, then you'll have a separate equation of conservation for the x, y, and z components, all right? Now, if it's an elastic collision, or if the energy loss is given or it's asked for, like 3 joules is lost, okay, so that kind of thing, then your kinetic energy equations are also important. So you find your initial kinetic energy and you sum to get your total kinetic initial energy, repeat that for the final. And if it's an elastic one, you set initial equal to final. And if it's not, then you'll have to solve for the loss. And sometimes the algebra isn't fun, and that's life. Okay, scattering angles and impact parameters. This was covered on the last day. So here you see a hard sphere target where you have an incoming projectile at impact parameter B striking a sphere. This is hard sphere scattering, folks, so you're assuming that impact is required. Because of the fact that it's not a dead head-on collision, it's not scattered straight backwards, but at some angle theta, which is dictated by where on the sphere it strikes due to geometry, okay? So what you can really measure for a scattering experiment, is the scattering angle and the number of scattered particles and the number of incident particles. And from that, you can deduce all kinds of interesting things about the system if you use the following math. So first of all, you need your target density, N sub tar, which is the number of targets per unit area. A is the total area of your target assembly. Sigma is the cross-section of each target as seen from the front. For a sphere, that would be pi r squared because it looks like a circle from the front. And then the density of the targets, N tar times A times sigma, will be the total area of all your targets. It would be really the number of targets, right, which is N tar, the targets per unit area, times the area. So that's just the number of targets, times the cross-section, which is the area per target, okay? Now, the probability of striking a target if you fire randomly would be equal to the area of the targets divided by your total area, which would be N tar A sigma divided by A. And that, A's canceled out, is equal to N tar times sigma. Now, you can also measure your probability directly by measuring the number of particles scattered and dividing it by the number of incident particles, N S sub C divided by N incident, and that equals your probability too. So you can set those two things equal and solve problems with it. Remember that the barn is a unit of cross-section, like it's as big as a barn, and one barn is 10 to the minus 28 square meters, okay? And we did a couple of example problems with this. We did one about scattering from an aluminum foil target, and we also did one about shooting a bunch of crows in a tree, which was a little bit more morbid, but also slightly funner. Okay, that concludes the Tobacco Auctioneer's half-hour tour of everything that we have done in the last couple of months. I hope you enjoyed it, but if not, you know, that's what tobacco auctioneers feel like too, I'm sure. So, enjoy your day. Let me know if you have any questions, and I'll see you in class.